workshop is Felix Ahnefeld, and he'll talk about coherence in phase estimation. Yeah, stage is yours.
All right, thanks a lot for the introduction. So, yes, let's dive right into the last talk of, unfortunately or sadly, this conference. I mean, not the conference itself is unfortunate, but that is the last talk, of course. So, I want, like in the last 20 minutes now, I want to give you kind of like an overview of our ongoing work on like coherence as a resource that quantifies the performance of phase estimation itself. And this is joint work together with Thomas Theurer and Martin Penio, who are both in the audience right here. And now, what is like the quick outline for the menu? I mean, it's late in the day, so let's keep it simple. First, I want to give a very brief crash course into phase estimation, and luckily, the previous speaker kind of did a great job of already like explaining this in a very generic setting of parameter estimation. We kind of make this more concrete for phase estimation itself, and then to actually analyze how well coherence benefits you in phase estimation, we want to take, normally I would say, a slight detour into defining incoherent prompts, but for this workshop, I guess that's not really a detour. And at the end of the day, we will kind of merge these things together and try to quantify the performance of phase estimation in terms of the coherence that is supplied. And this is kind of in line with trying to identify some resources, most notably coherence and entanglement in some algorithmic settings where you can actually essentially quantify the speed up in terms of these resources. Right, so let's take a slightly easier approach and let's consider so-called standard phase estimation. The premise is pretty simple. So you're given some sort of unitary in this form here. So in its eigenbasis, let's call it n. This essentially encodes eigenvalues, which are just rotations on the unit circle, of course, and these are just multiples of a single phase. And I give you this unitary. Your job is to find this phase phi. Now, let me stress that this unitary has like a dimension of n. And for the beginning, we will fix this now. In principle, this can be any number. I mean, any number larger than 2, please. And with that, we can do phase estimation. Now, we want to treat this as a black box, which means that, well, you can't do too much with it except for probing it. And you do this by essentially putting like this blue box around it, which is a quantum supermap, in case you are familiar with like the Cohm formalism and like how you graphically depict this, more or less in a second. And what you then additionally can do is you can probe this whole evolution with an input state rho, at the end perform a measurement, and from the measurement outcomes, let's call them x, you want to construct phase estimates that are aligned around the unit circle. So these phi x heads represents your estimates, and you want to optimize this performance. Now, optimize in what? We get to that in a second. But for now, let's take the detour to comps. Because, well, essentially, if we want to optimize this protocol, we kind of need to specify what we actually want to optimize over. And if you just optimize over all possible like quantum processes here in the middle, this problem has been solved like 10, 15 years ago. And like optimal phase estimation is pretty well known actually. But let's say you put resource constraints on the supermap. So let's say the supermap cannot create any coherence. Then what you will find is essentially that here in this middle part, there's absolutely no coherence present. And this unitary will just simply not encode any information about the phase. Good. That essentially means that any resource that you externally supply in the setting comes from your initial state rho. Right. And now let's actually characterize this middle block. Just as a quick reminder what that actually means, this graphical notation just essentially tells you that there's like a pre-processing channel N, a side channel that is passed through down here, and a post-processing channel M. So you kind of can construct the supermaps, like deterministic supermaps all the time. Good. Now, essentially it's not much more work to characterize like a supermap or like an entire comp. In case you're not familiar with that, that just essentially means like having a big supermap with multiple inputs, multiple outputs. And here in this notation, you essentially label the input systems by even numbers, so 0 to 4 up to 2m, and the outputs by odd numbers, so 1, 1, 3, 5, 2m plus 1. So this comp, quantum process, quantum Lego, however you want to call this, this can essentially transform m copies, m different channels into some other, well, in principle, n different channels. Right, now, if you're familiar with that, that essentially mathematically boils down to just characterizing this object down here I mean, just in its Choi representation, or Choi-Jamalkovsky representation, I should say. And that is given by a sequence of positive operators, which satisfy this normalization condition, which also enforces causality on the structure. So you have a clear distinction between what is an input, what is an output in that setting, okay? Now, what if you kind of want that the structure cannot generate any coherence? And let's do this quite intuitively first. Let's say you compose it with two complete dephasing operations at like port 0 and port 2. Just as a quick reminder, this dephasing operation essentially deletes all resources, either static, so either states that you enter, or dynamic, so channels that you enter. So say you would perform a Fourier transformation at the beginning, then do the dephasing, there's no coherence left. That just gets murdered. That means no coherence in, like at ports 0 and 2, and intuitively, this should also mean there is no coherence at output ports 3 and 5. And that essentially boils down to having this composition with the dephasing at port 1 and 3. Good. So that's kind of the intuition behind it. Essentially, it's just a matter of nothing in, nothing out, but in a sort of causally ordered manner. Right, so far so good. And if you actually do the math and kind of impose that this blue thingy here transforms like maximal incoherent channels into maximal incoherent channels in a complete sense, to be precise, then you will find that in order for that to essentially define a free or incoherent comp, you need this additional condition here on the sequence of Choi operators of the supermap. Right. Just as a quick sanity check, and I mean, that's quite a mouthful. Let's take a simpler case and just consider the specific example of where you essentially like, collapse all of the structure down to one simple channel from like system 0 to 1. And then that's just literally the Choi representation of a simple channel that transforms any incoherent states in 0 to any incoherent states on system 1. Okay? Good. And that's what we kind of want to use as our set we want to optimize over our blue box in this setting here. So this blue box is subject to being like free in the sense of these conditions on this slide here. Good. Now, let's come back to phase estimation. In the previous talk, we have kind of seen phase estimation in the light of like a metrology setting. But you can use phase estimation more broadly than that. And for people that are familiar with that, phase estimation is a subroutine in quite a lot of quantum algorithms. Probably most famously, Shor's algorithm. So if you want to do integer factorization, then essentially your job is to guess a phase, and you can sort of tolerate little deviations from this phase without any penalty. So simplifying a bit, if you can guess this phase within like an epsilon interval around it, you're perfectly fine. But as soon as you go out of this interval, well, congrats, you won't do anything with it. And essentially, this is one aspect of an example where there's like not a unique way to quantify how well phase estimation works. And the other one, I mean, would basically be the variance, like in the previous talk. And what we kind of decided to do is to just take a generic cost function, where we just simply impose that this cost function, please be positive. So, well, we get penalized somehow. And this cost function better be zero if and only if, well, the phase you want to estimate is actually estimated exactly. This condition is actually not necessary, but for simplicity, we just take it here for this talk. Now, what we then look at is the average cost. So basically, you have this cost function, average over, I mean, your measurement outcomes and some prior distribution on this phase phi. Here it's a uniform distribution, meaning that, well, we have no clue what this phase is. And we want to minimize this average cost, which we call Cn of rho. We minimize that over all these blue boxes, all measurements, and also all possible like classical assignment rules in which you can kind of assign a parameter from your measurement outcomes. Good. One quick note. Of course, this average cost kind of depends on the dimension of your black box, because, I mean, if you kind of encode your parameter more refined on the unit circle, then I guess it's quite intuitive that if there's like a more finer graining, then you will be able to guess that more accurately. Good. So moving on, what do you find in this setting? So essentially this optimization from the previous slide, so this thing down here, can be reduced to a semi-definite program where you essentially just optimize over a single channel in mu with respect to an objective function that encodes this xn here. And this xn is what we call like the cost function. That's essentially, cost matrix. That's essentially just a matrix that encodes like all of the possible Fourier coefficients of the cost function up to a certain degree. And I mean, forgive me if I kind of mistake this cost matrix and this cost function in this talk. And I will just probably use them interchangeably from now on, because they're more or less the same. At least from the cost function, you can always get the cost matrix, and at least asymptotically for n to infinity, you can also recover the cost function from the cost matrix. Good, so far so good. To summarize this very briefly, I mean, this gives you kind of a way to actually compute the average cost. And also, it immediately tells you what the optimal protocol is. So what you will find is that essentially you can throw away the side channel down here, perform an optimal pre-processing of your resource state rho, and at the end perform an inverse Fourier transformation and measure in the invariant basis. There's essentially just like the so-called standard phase estimation, like it has been proposed originally by Kitaev and I think only Kitaev actually. Right. But how much does coherence actually help us? To kind of start this question, let's start it very easily. I mean, for this SCP, you can find some very trivial bounds. So first up, if you just simply drop any constraints on the resource, so you just throw away this mu constraint here and optimize over all possible channels, I mean, what you will do is you just project on the minimal eigenvalue of this xn. And it turns out, I mean, these cost matrices are triplets matrices. They are very well studied, and this minimal eigenvalue is not vanishing, first of all, and it decreases in n. So just as you would expect, more dimension of the oracle, more oracle queries, better performance. And an upper bound is simply given by this x naught naught, which is just the like constant contribution in the Fourier expansion of the cost function. Now, I should probably say that this upper bound is saturated by any possible incoherent state. So like having no coherence, you basically always turn to this constant factor here, and your estimates rather turn into like pure guesstimates. But the question is kind of what happens in between. I mean, you have this like constant scaling, and you have the scaling, which kind of spoiler, decreases in 1/n². And to do so, first of all, to do so, you can first of all define a family of monotones. And a family because, first of all, it depends on the dimension, so it depends on n, and it also depends on the cost function here. And these monotones, Mn, they directly quantify how much your average cost actually decreases if you have something resourceful. Now, I mean, based on this definition, surprise, surprise, this is a convex monotone. That's not really the hard part. And also not really, I mean, also the interesting part, but what's really interesting is that these things are what we call quasi-faithful, meaning that for any incoherent state, well, they vanish, and you again saturate this bound here. And for any state that is somehow resourceful, these things are actually larger than 0, given that your cost function is like non-constant and your dimension is sufficiently large. But I guess that's kind of a fair assumption, and that's why we also refer to them as quasi-faithful, right? Can you go a bit further than that? Actually, you can, because you can kind of separate the problem into, or you can separate the bound on the average cost into like a factor that depends on the problem itself and one that depends on like how much resources you have at hand. And let's just look at the first line to begin with. So essentially, this average cost is bounded from below by the minimal eigenvalue of x. So remember, that's your optimal attainable quantum performance. And whenever you lack some coherence, because, well, either you lost it during the protocol, should be a bit careful with this phrasing, but let's say you can model it as losing it during the protocol, turning it into the initial state. Then you kind of pay an additional factor of this minimal eigenvalue of the off-diagonals of x times the generalized weight of coherence. Okay? This essentially means that whenever you lack coherence, your average cost will automatically increase, so phase estimation is worse. And turns out, because these Stiglitz matrices have been studied to death, I mean, like their spectra are known extremely well, it's quite easy to show that these minimal eigenvalues are essentially bounded by a constant over n², and these bounds kind of turn into something that looks like a Heisenberg limit. So essentially you have like this optimal attainable bound plus something non-vanishing, which penalizes how well you can actually get to this Heisenberg limit, and how well you can get there is measured by this weight of coherence. Right. I'm running out of time, so let me give you a brief example. Like one very specific cost function is like periodized variance on the unit circle, and there you will find that if you just calculate this for a rather small dimension, then you have this optimal attainable quantum bound, which, remember, larger dimension, this one will decrease in n², and like all of like a bunch of randomly sampled states will lie above this weight bound. Now, this first of all also gives you kind of a nice application of like weight monotones and in coherence weight to be more precise, and it gives you actually like an operationally meaningful and actually applied thing to do with it, rather than state exclusion only. But it also kind of separates this problem nicely into problem-specific and like purely resource-specific part. yeah, maybe one quick note on like the very, very generic phase estimation protocol, because often you are given not only a single oracle, but like multiple copies of a qubit unitary oracle. That's also why we did this like comp stuff in the beginning. Essentially, you can just kind of process all of these like copies in terms of an incoherent comp, throw in some resource state and do the same analysis. And I mean, it has been known for a while that like if you don't have any constraints on resources whatsoever, then this all collapses to just standard phase estimation. So the case which we covered in the last 20 minutes. It seems like the same is also true for the coherence constraint case with some slight caveats. Right, then let's get to the summary. So essentially, if you consider phase estimation with some generic cost function, can be more or less whatever you want, you will find that coherence essentially emerges as a like quantifying resource in how well this protocol works. And also, you find that like a family of coherence monotones directly quantifies the performance. You can also kind of read this like the other way around. So if you have some coherence, you will always find like a stupid cost function where you get a benefit. But I guess that's kind of cheating because this cost function, if you want, is essentially associated with the task you want to solve. So remember, if you want to do metrology or if you want to do integer vectorization, the cost functions are very different. Right. Yeah, then probably, yeah, some open problems. I mean, what happens for a non-uniform prior for noisy encodings? To be fair, no clue what happens, but would be interesting directions to explore. And I guess I'm over time already, so thank you a lot, not only for your attention, but also for this entire great workshop.
Thank you for the live talk. Questions or comments?
Thank you. Some really interesting ideas there. I guess micro is often phase estimation, of course, is motivated by things like short output, so there's a heavy computational complexity there. But it looks like in your work, the optimal protocols for estimating phase is inherently scales polynomially with system size, so they're inherently efficient. Do you think this is always the case, or is there certain estimation problems where we could still cast in this framework, but to achieve optimal estimation involves a circuit that scales exponentially? So what happens if we actually build in computational component to it? That feels here though, everything is efficient.
So just to clarify if I understood correctly, like, do you mean phase estimation protocols or like generic parameter estimation?
Generic parameter estimation.
Yeah, honestly, I don't expect this scaling after all. I mean, this is very specific to phase estimation, and even worse, actually, like specific to this like perfectly unitary encoding. If you go away from that, I don't think with that you can say anything.
But with perfectly unitary encoding, we do have efficient circuits generically.
I don't know. I think that's quite a hard question, but I mean, of course, would be lovely to explore.
Thank you.
Any other questions? Okay, I just have one. So you mentioned about there is a minimum number or dimension that you have to guarantee the faithfulness. Is it a calculable quantity, or how does it scale by some choice of the questions?
Yeah, so essentially it's perfectly calculable. So the structure, I mean, the explanation basically lies in the structure of these cost matrices. So you essentially just have like the Fourier coefficients of the cost matrix, and you just arrange them on like these side diagonals, right? And let's say your cost function is just a simple polynomial, but like the Fourier modes only start at like whatever n is equal to 10. So of course, this matrix is simply gonna be empty, except maybe for the diagonal, and only after this like mode n is equal to 10, the benefit kick in. So yeah.
Thank you. Any other questions or comments? Oh, if not, then let's thank our speaker.